John, it's your turn, sir.
Okay. Thanks, John. My pleasure to be here today. Paul did a very nice job. Thanks, Paul. And I'm going to be talking about soil water. You know, we know that's a real limited resource while I've been in this drought. So I'm going to be talking about, I'm going to give you some basic understanding of some soil water, and because I think if you understand some of the basic principles, then you can think about how do you integrate that into your system. And then secondly, I'm going to cover some work that we're doing on trying to manage water more intensively in our wheat, sorghum, fallow type systems. And then I'm also going to lastly touch on some long-term comparison of tillage and no-till. Yeah. Okay, there we go. Lastly, I'm going to talk about some long-term, about some tillage work we've been doing in western Kansas for the past 20 years. Originally, fallow was not part of this area, if you can believe that or not. Well, how did we get there? Well, you know, fallow really helped stabilize crop yields. We especially saw that in the 30s. 50s was a bad time for drought, and now we're in the middle of one of those historical dry periods. So it's times like this that fallow really shows its value. If we look at this as available soil water, and then with winter wheat yield, and as you can understand and know, as we increase the amount of soil water at planting time, our yields go up. And so what we need to do is try to manage that precipitation real effectively so we can get good yields. When we talk about term precipitation storage efficiency, simply what that means is it's how much precipitation you get during the fallow period that you're able to store and put back in the soil. So you want to put as much rainfall as we get in the soil so we can have more water to work with. There are a lot of things that affect precipitation storage efficiency. Paul did a really nice job talking about residue. Residue and tillage are really critical. Other things are air temperature and wind speed in our area in particular. Hot temperatures, high winds dries out the soil. The timing and amount of precipitation. Those precipitation events that are less than 1/10 of an inch or greater than 2.5 inches, you know, those are not very effective rainfall. Soil texture and infiltration rate affect that. And then also time between precipitation events. Those are all factors that affect how we store our soil water. This is some data looking at Tribune, Kansas, with different tillage methods. First of all is the no-till, reduced till, and conventional till. And if you look at the efficiency on the far right column, this is in a wheat fallow system. So what this is showing is during that fallow period in no-till, we stored about 24% of our rain. That means we lost 75% of our moisture due to evaporation. We lose a lot of moisture due to evaporation during that fallow period. Reduced tillage was not quite as effective. There we're only storing about 21%, and when we till the ground quite a bit, now we're only storing about 12% of that moisture. So less tillage, we're going to store more soil water. This is showing the effect of till and no-till. The black, across the bottom, there's different tillage treatments. We have moldboard plow, conventional till using sweeps, reduced till system, and then no-till. The black bar is 0 to 2 days after a tillage event, and then the gray bar is 3 to 5 days after a tillage event. So when we go out there and till the soil, we have a real rapid loss, immediate loss of soil water. We burn off a lot of soil water real quickly. Now over time, that amount of loss is going to come back and be about equal to no-till. But every time you go out and till, we get a real rapid loss of soil water. It dries out that soil. So the other point to make here is even though it's no-till, you know, we're still losing soil water due to evaporation. Now this is looking at the precipitation efficiency during the fallow period of a wheat fallow type rotation, and looking at the time of the year as we go through a wheat fallow system. So this is showing it for conventional till and no-till. The conventional till is in red and the yellow is in no-till. So we have that first summer period after we harvest the wheat we're storing between 20 and 30% of the moisture. We go through the winter period, which is a lot cooler time of the year, and so our evaporation loss is less. Our storage efficiency is a lot better. During that time of the year, in no-till, we're actually approaching 80%. Storing 80% of that moisture during the winter months. The second summer period, we roll around, and then prior to planting wheat, this is showing much less. Actually, there's quite a few studies, and I can show that actually that number is negative. We're actually losing more soil water that second fallow period than what we're receiving or storing. So what this means is, in a typical year, a wheat summer crop fallow rotation works very well, because as we roll around to that second year, we're actually losing more water than what we're storing oftentimes. Now, when we're in a historical drought, that's a little different situation. We just barely have enough water to grow a crop. A lot more fallow in that can work. So when we're in a situation of less than 14, 15 inches of annual precip, wheat fallow tends to do better. But in a typical year, our 24, 26 inches down to 15, a wheat summer crop fallow is why that rotation has really caught on in the last 20, 30 years in the area. Looking at, Paul talked about this too. Now this is looking at the amount of residue out there. As we increase our residue level, and this is across a whole bunch of different sites across the Great Plains, as we increase our residue level out there, we do a lot better job of storing precipitation. So the more residue out there, the better job we're going to do at being able to keep that rainfall we receive. The type of crop has an effect. This is comparing a wheat sorghum fallow to a wheat sunflower fallow. So the only difference here is just that summer crop grown. You can see with sorghum, which does a nice job, more residue out there, covering the ground better. We're storing about 20% during that fallow period after the summer crop, compared to sunflower, where we're storing about half that amount, only 12%. Corn would be somewhere along the lines of sunflower. So grain sorghum does a nicer job of covering that soil and reducing evaporation and storing soil water. This is just showing the effect of, here we have water storage on the left, with wheat residue across the bottom, increasing in amount of wheat residue, and then sorghum grain yield on the right column. So this is, the yellow bar is the water storage, and the red bar is the yield. So as we increase our wheat residue, we're increasing our water storage, and we're increasing our sorghum yield. So residue is, again, very, very key. Now if we look at, in our wheat summer crop fallow type phase, looking at that fallow period after the summer crop is grown in that 3-year rotation, if we look at when we harvest that summer crop to the following July, we're storing about 28%. But if we look at from July to wheat planting, we're oftentimes actually, and in this case, we're actually losing ground. We're actually storing, not storing any more soil water, and we're actually losing water out of the soil profile. When we look at the total fallow period, we're at 21%. So what this means is we have an opportunity here where we went from wheat fallow to maybe a wheat summer crop and doing something in that third year of fallow period, and that's what I want to talk about going into next. So we know, again, wheat fallow is inefficient. Now, given if we're in a record drought, we need fallow, okay? But on a normal type situation, wheat fallow, I showed you, we're not doing a very good job of storing water in that second year, so a summer crop works great. Same thing in that 3-year rotation. That third year, we're actually not doing a very good job of storing soil water that third year. So can we grow a short season spring crop that third year and be able to do a better job of managing soil water? And so that's some work I'm going to show you. And so what that is really we're kind of looking at a flex fallow that third year, where if you've got a lot of good water in that springtime, consider growing something. So can we strike a balance? We did a study looking at some flex fallow from Garden City. Garden City averages long-term about a little over 18 inches. But during the course of this study, we're at 16. In the last 3 of the 4 years of this study, we're down around 13 inches. So this is some awfully tough conditions to look at flex fallow in that kind of a situation. Now, we looked at a whole host of winter and spring crops grown in that during that fallow phase ahead of winter wheat, and we grew cover crops. So you've heard often, I'm sure all you have heard of cover crops. We looked at cover crops, we've looked at hay crops, and we also looked at spring peas for grain. This is just showing soil water storage, comparing cover crop and hay. The cover, and this is looking at the second column is in the 0 to 3 inch profile, and the third column is in the 0 to 6 foot profile. Cover is storing about 0.8 inches or less than an inch of water more than hay, okay, when we compare the two systems. But now we'll look at some of the individual treatments. Fallow, this is comparing all these different things we looked at, and so you can look at that. But fallow, the far right column kind of does a nice job of showing it. Fallow was the best. Fallow stored the most soil water, more than any cover crop out there. Now, if we look at the spring type crops that weren't grown for a longer time period, they resulted in about 1 to 2 inches of less soil water than fallow. If we looked at the winter cover crops that were grown for a longer period of time, they were reducing our soil water about 2.5 to 3.5 inches. And then we also had a pea grain and a continuous winter wheat treatment. So the very intensive continuous winter wheat, we had about 5 inches less water to work on. I want to show you oftentimes maybe hear about cocktails and how, well, if you grow one cover crop, it doesn't store soil water, but if you grow a cocktail, magical things happen and we store soil water. So this is in a different study we've had going on to address that question. With cocktail was a 6 treatment study, and you can see compared to fallow, cocktail is that second treatment up from the bottom. It had about 4.5 inches less soil water than fallow. If we look at crop yield over across the 4 years, fallow is in the far right. And then we have continuous wheat, which was the lowest yield at 33 bushel. Wheat fallow averaged about just under 60 bushel. You can see a lot of these treatments are quite a few of them, especially the spring, growing something during that springtime, are yielding very similar to fallow. Now, if we're growing a winter type crop in there for a longer period of time, our yields are a little bit less than fallow. Now, let's look at some economic numbers. So this is showing the economics of, and really look at that bottom line, best alternative. What I have here shown is a returns from growing a cover crop, a hay crop, a grain only if that was continuous winter wheat, or growing peas for grain, and then the best alternative. So anything in red, and this is comparing it to a fallow, and I figure during that fallow phase it's costing us about a little over $40 an acre just to fallow. So if we lose less money than fallow, we're making money. And what this shows is growing a hay crop in there. The cover crops always lost more money than fallow. We always lost more money with the cover crop. But if we grow that crop for hay, we're making a little bit more money. And actually grain peas, we're making a little more money. And in northwest Kansas, grain peas is really starting to catch on in that third year. Now, they've had a little more moisture. They've had normal moisture to work with a little bit more than we have, where we've had a lot less. And that kind of rotation is really kind of starting to catch on up in northwest Kansas. So I think we have some opportunity in that third year, if we have moisture, to grow a hay crop or grow grain peas. Next, I want to talk about some real long-term results from 1990 to 2012, looking at soil, water, and grain yield and tillage systems. So how do these comparing conventional, reduced till, and no-till for over 20 years in western Kansas? So this is available soil water at wheat planting. Reduced till and conventional till were very similar, and they had more soil water to work with than conventional till. If we look at the decadal yield from 91 to 2000, and then we have 2001 to 2010, and then we have the long-term average for both conventional till, reduced till, and no-till. And you can see no-till has always done better than reduced till or conventional till. But an interesting thing we're seeing is that the difference is actually increasing over time. Initially, no-till did about 22% better than conventional till in the first decade, but in the second decade, it's actually 61% better. So we're actually seeing more spread between tillage systems as time goes on. This is available soil water at sorghum planting, very similar to wheat. Reduced till and no-till have similar soil water and more soil water than conventional till. Now we'll look at sorghum yields. Sorghum actually responds better to no-till than wheat. In the first decade, no-till was 71% better than conventional till, but in the second decade, no-till was 256% better than conventional till. So, boy, I tell you, sorghum and no-till pays if you're growing sorghum. Looking at available soil water, there's about 1.5 inch difference, more soil water available in reduced till, no-till, and conventional till. But when we look at yield difference, we're seeing that no-till yields are a lot better than reduced till. So soil water is not the only key, and part of that is shown in this graph here. What this graph here shows is we have the available soil water. It's kind of hard to, let me kind of walk you through this. So here we have the beginning soil water, and for the top one is conventional till and the bottom one is no-till. And reduced till is kind of in between these two extremes. In no-till, we're starting out the situation with better soil water than conventional till, but the slope of this line is steeper. So what that says is we're actually getting a better use out of the rainfall during the growing season with no-till than reduced till or conventional till. So we're storing more soil water, and we're getting better use efficiency out of the water in the growing season. Now that's the case with wheat, and that's also the case with sorghum. Looking at long term, this is some economic data using 2010, 2011 market price and costs. You can see that during the first decade, how these treatments broke out. No-till doing a little better than reduced till or conventional till, and then in the second decade, we actually show that we're losing money with either reduced till or conventional till, and been making some money with no-till. With that, I hope we start to getting some rain and have a crop that looks like this. So.